The Simpletons' quadratic staircase of infinite descent for the sum of two squares, to demonstrate how the sum of two integers squared results in an all-integer number field only of integers of modularity 4n plus 1, which, despite its apparent disorderly array, is underneath it all anything but disorderly. My motto? Plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. The Simpletons' mathematical coat of arms. In Euclid we trust, but not the mathematicians. The main purpose of this relatively short presentation is to give you, the viewer, a deep yet simple and intuitive understanding of how the sums of two squares develop from the bottom up, or in the case of the diagram, which I have named the Simpletons' quadratic staircase of infinite descent, from the bottom down. You may or may not be aware of the fact that professional mathematicians, just because all the primes of modularity 4n plus 1 we know of happen to be the sums of two squares, do not accept it as proof that it is true for the infinity of all 4n plus 1 primes. I hope by the end of the video that, like me, you will disagree, even though until recently I also was of that opinion, but not anymore. We start with the diagram shown, which is little more than square concentric rings expanding outwards to infinity from a common centre. So what we have is 2 squared consisting of 4 yellow unit squares at the centre, then an outer ring of blue to make up 4 squared, then an outer ring of green to make up 6 squared, then 8 squared, 10 squared, and an outer ring of green squares to make 12 squared, and so on and so forth ad infinitum. As our sum of two squares must consist of both an odd and an even square, and since we are starting with even squares, we are only seeking odd squares to pair with them, so we proceed in the following stepwise manner. 1. Our top step is 2 squared plus 12 equals 4 squared, whence we find 2 squared plus 1 squared equals 5, and 2 squared plus 3 squared equals 13. Which are the only two sum of two squares less than 4 squared equals 16. So we have our first step, which is 2 spaces high. 2. We start a new step, which is 2 squared plus 12 plus 20 equals 6 squared, where 20 is the difference between 6 and 4 squared. Starting again at 2 squared and continuing where we left off, we see that 2 squared plus 5 squared equals 29. Is less than 36, but that 2 squared plus 7 squared would be too big. Next, we see that 4 squared plus 1 squared equals 17, and 4 squared plus 9 equals 25 are okay. But again, 4 squared plus 7 squared is too big, so we have our second step with 3 spaces. 3. We start another step, which is 2 squared plus 12 plus 20 plus 28 equals 8 squared. So we now have 2 squared plus 7 squared equals 53, but 2 squared plus 9 squared is too large. What we do have are 4 more solutions, starting at 4 squared plus 5 squared equals 41, and ending with 6 squared plus 5 squared equals 61, giving the step with 5 spaces. 4. We start another step, which is 2 squared plus 12 plus 20 plus 28 plus 36 equals 10 squared. So we can now obtain 7 solutions, starting at 2 squared plus 9 squared equals 85, and finishing at 8 squared plus 5 squared equals 89. All composites are highlighted grey/yellow, all other entries being 4n plus 1 primes. 5. We obtain 7 solutions for 2 squared plus 12 plus 20 plus 28 plus 36 plus 44 equals 12 squared as shown. For the steps 14 square and 16 squared, we have 11 and 10 sums of two squares respectively. 7. We can continue like this building our steps ad infinitum. Note that 16 plus 9 equals 25, highlighted yellow, is the first and smallest all-integer Pythagorean series privative triple. 16 plus 9 equals 25 equals 4 squared plus 3 squared equals 5 squared. The next one is 144 plus 25 equals 169 equals 12 squared plus 5 squared equals 13 squared. The Pythagorean series contains every odd integer from 3, 5, 7, 9, 11 and so on to infinity as the smallest odd squared term, and therefore every possible 4n plus 1 and 4n plus 3 prime in the infinity of the integers. Similarly, every output of a triple has modularity 4n plus 1 and includes every square of primes of modularity 4n plus 1. So if the square is present, then so too must be the 4n plus 1 prime root. So I hope, like me, that you feel spiritually revived mathematically speaking, and do not require reams of abstract Picasso mathematics that nobody can understand in order to be told by the high priest that the sum of two squares conjecture is true. The Fermat-Bateman triangle slide that soon follows does what the staircase method achieves, but in a somewhat more formal way. To summarize, the Simpletons' quadratic staircase of infinite descent for the sum of two squares is in effect a prime sieve, just like the sieve of Eratosthenes, except that it only sieves primes of modularity 4n plus 1. Well, no, it also sieves 4n plus 3 primes, since all the even powers of 4n plus 3 primes are factors in the number field, that is the sum of two squares. No one speculates that there may be missing primes for the sieve of Eratosthenes, so why do we for the sums of two squares? The formal Fermat-Bateman triangle for the sum of two squares produces orderly rows of numbers that increase progressively in magnitude along the row, although we see that the start of any row is smaller than the end of the row before it. As the numbers and therefore the rows get bigger, this situation will occur over more and more smaller rows, and the situation will be made worse by composites that have multiple sums of two squares that cause further disruption to the uniformity of the number field. We get a disorderly number field from the start with the staircase method. On page 392 of Elements of Algebra, 1770 by Leonhard Euler, we read his remark, "Farther, every prime which belongs to the formula 4n plus 1 is the sum of two squares. This is undoubtedly true, but it is not easy to demonstrate it." A footnote at the bottom of the page, presumably due to J. Bernoulli, attributes a proof to Gauss and to de Lagrange. Why not to Euler himself, who had also published a proof in 1760? Euler's proof is available as a free download from the Euler archive, EN 241. This has been rehashed as a modern update in Wikipedia, in which the second statement states: 2. If a number which is a sum of two squares is divided by a prime which is a sum of two squares, then the quotient is a sum of two squares. Wrong. 45 equals 6 squared plus 3 squared equals 9 times 5, and 5 equals 4 squared plus 1, and 45 over 5 equals 9, which is not a sum of two squares. End of video.